Hi and welcome back. It's been a while since I have posted the last video, and it was commenting about what we are about to discuss right now, which is this method, Denavit Hartenberg, which is, as you will see, uh, one of the most important methods or techniques to analyze robots. So from here we will see this method, or we can also call as a technique, just like representations of the with the Cartesian system, representations with the cylindrical system, with the spherical system, all these types of representations of a robot. Those are techniques or methods. And I have drawn this this figure, which is a representation of a three articulations and two links. And we will use this figure, this representation, to discuss about this technique. And also, it's better if we start since the beginning. So let me just introduce to you to this technique, to this method, which is Denavit Hartenberg. Actually, Denavit and Hartenberg was a physicist and professor and a mechanical engineer. Denavit, his name was Jacques Denavit. Sorry, Jacques Jacques Denavit, and he was a physicist and a professor, and Hartenberg was a mechanical engineer. And they wrote an article, and it was about how to represent and modulate robot. So they present this method on its article. And also this method, it was used to derive equations of motion. So they developed this method and on this article, and to these days we are using this method or technique to do modulations of the motions of the robot, and this method is what we say that is the standard method to modulate and derive motions of the robots. So let me write this DH, which is the abbreviation of Denavit Hartenberg. What is used for? What DH method is used for? Let me change this color. Okay, so is most used for modulate robots and its motion. So we are dealing with things like the links of the robot, so the links and the articulations, which is the joints. Articulations, which is the joints, is the joints. And this model, method, sorry, or technique. So this method or technique also can be used to represent transformations. So this is why you will see that this is one of the most important methods to analyze robots. Um, we got methods like the Cartesian one. When I mention representation, I'm referring to the way in which this robot is being represented on a 3D space. We got Cartesian robots that can be represented in two-dimensional space, X and Y, but this robot is in a real world in 3D space. So we got these methods or techniques, ways to represent this robot in a space. So we already has studied this method, which is the Cartesian one. So we got the Cartesian coordinate system. We also got the cylindrical coordinate system, the spherical one, and Denavit Hartenberg is a method that we can use to represent both of these robots, even that this robot is in a Cartesian coordinate system or in a cylindrical or a spherical one, we can use Denavit Hartenberg, and also to robots with one more than 2, 3, 4, 6 degrees of freedom with n links and joints. So this is what we are about to discuss. It also is used to represent transformations. Transformations in any coordinate system. Okay, so let me just write this. We already has discussed this. Cartesian. These are the coordinate systems. Cartesian one. The cylindrical one. The spherical one. And all this with addition of the RPY and Euler. So with DH representation, we can represent with DH, we can represent any possible combination of articulations and links. Now, what is important to comment is the benefit that we got using the Denavit Hartenberg representation instead of the ones that we already have studied, which is the representation with these coordinate systems right here. So let me write this in a different color because it's important. The DH representation it has the additional benefits and let me list these benefits. So using DH we can do the analysis of differential movements. So we can do the analysis of differential movements. It's best if we say that movements or motions. I think is correct. Movements or motions. Also, we can do the analysis of motions, Jacobian motions. We can do dynamical analysis and we can do what is directly related to dynamical analysis of forces. And robots got a characteristical, and when we use this representation DH, we can cover these characteristics of the robots. Like, let me change the color because it's important. Robots can be made of a succession of articulations, the joints, and links at any order. Or in any order. I think in any order. And what they can do, what they can do. So they can move in different planes. They can have links in any length. They can be twisted and bended. And also they can be any plane, be at any plane. And with that being said, what we need is we need to be able to model any robot configuration. So we need to be able to model and analyze any robot configuration whether this robot or not, it follows any of the preceding specific coordinate coordinates. And now to do this, what we have to do is establish a procedure. So just like any other procedure, what we will do is um, write a list with steps that we need to follow to accomplish this task. So to do this, to do this, let me write to a model to modeling and analyze any robot configuration. Sorry, to modulate to modulate and analysis analyze to modulate and analyze any robot configuration. Configuration. We will follow the respectively steps, follow the respective steps. Okay, so now, and of course I'm using um, the context of the book, which is the third edition. And again, if you have the opportunity to grab this book, to have this book in hands, um, is highly recommended. It is a very nice book, as you can see. So what we're going to do is assign a reference frame to each joint and use a general procedure to transform to transform from one joint to the next. Which is one frame to the next frame. And the list is very short with two items, but within each of these items, we got more steps to follow, and we will develop this when we start to solve the problem. A example. Now let me draw a example that we can use to describe what I'm about to write, to explain um, this procedure. So we need to now learn how to write transformations, use DH representation. So we can use a example. So again, let's draw a, a robot with n links and joints. So right here we got a base, we got one link and two links, three links, and four links. And we got these joints, and of course a end frame. Now let's name each of these links and the end frame. So we got the end frame, we got the base, and let's call this base as referential, so R, and the joint 1, the second joint, joint 2, and the third joint, joint 3. So if we combine, so let me write this because it is important. If we combine all the transformations from the base to the first joint, from the base, like you are seeing right here, this base to the first joint, and from the first joint to the second joint, and so on and so forth. From the first to the second, until we got to the last joint. We will have the robot's transformation matrix. We will have the robot's total total transformation matrix. And at this point, we got at least a sense on how to do this. Um, so this is something that we already has discussed on the past. Um, even if we don't we don't name it these joints or know the quantity of links and joints, even that we do not know the task that this robot is performing, we can write its total transformation because it's always referenced to the end factor related to the base of this robot to its universal frame, which is the referential frame. So remember that we can write, as I'm saying, this first transformation, which is the total transformation, is the transformation of the frame E in relation to the frame R. And this transformation is the result of both transformation that is happening on this robot, which is describing its motion. So transformations, they are also referenced a to a referential frame, to a reference frame. So as you can see right here on the joint tree, of course we can attach a referential frame, a reference frame, so we can, which is the moving frame. Um, even if you are reading a book, illustration of a robot arm, any illustration, and this illustration, you do not have the representation of the moving frame with its coordinate system, with its reference based on its axis, like right here we can have, or something that we already know, which is this moving frame made it with the axis, sorry, made it with the axis A, O, and N. And right here we can also again attach it this reference frame, and this reference frame is not fixed like this one. This one is fixed, so this one is the reference frame that we call XYZ, and this one is fixed, and these ones, they are movable. So to each joint we can attach this reference frame, which is referenced to this uh, XYZ um, fixed frame. So right here again, AON, and we can write um, again. We always need a reference to write a transformation. So we can write right here that we can do a transformation of the E frame in relation to the frame J3, and the total transformation is a product of all transformation on the system. So now is we can write a transformation of the frame J3 in relation to the frame J2, and we can also write a transformation of the frame J2 in relation to the frame J1. Okay, and this is what is being said right here. If we combine all the transformations from the first joint to the second joint, and so on and so forth until we got to the last joint, we will have the robot's total transformation matrix. And of course, will depend on the coordinate system uh, in which we are in which this robot is placed. If it is on the Cartesian, on the cylindrical, on the spherical, but right here again, using the representation DH, we can cover both of these coordinate system. Okay, I try to explain what we can do with the DH representation and why we use. And now we need to get back to this figure. And with this figure, we can abstract more things about DH representation. And I will repeat again, is one of the most important ways to represent robot and its motions, and it is considered the standard way that we can do this. This task of represent, do modulations, analysis. Okay, so as you can see right here, we have this joint. So this one is a joint. A joint. This one is also a joint. A joint. And right here, the links. A link. Just a link. Okay. And what we are doing is assign the joint number as n. So this one is the joint n. And this one is the joint n plus 1. And this one is the joint n plus 2. Okay, that is right. So we have named this joint as n, the second one as n plus 1, and this third one we are naming assign as n plus 2. And again, using the DH representation, its benefit is that we can represent, do modulations, analysis of a robot with any number of joints and links. So right here we can have joints, more joints before or after these ones. We are naming these links also. So we are naming this link as link 1 and this one as link n plus 1. Link 1, sorry, link n, we are naming as link n and link n plus 1. And now let's take this procedure that we have listed with these steps. So where's the list with these steps? Okay, right here. So the first thing that we need to do is assign a reference frame to each joint. So let me copy this list and we will do just a check-in. Let's use as a check-in list to verify on this illustration these conditions. So follow the respective steps. The first step, the first condition, assign a reference frame to each joint. So as you can see on this joint, as we are naming as N1, we are, as you can see, assigning a reference frame. We are assigning the z-axis, the x-axis, and further on this explanation you will see that we do not need the y-axis, just the z and the x-axis. So on the checking list we are verifying this first condition, completing this condition, which is assign this reference frame. And well, at this point you know very well what is a reference frame. Okay, although for moving frames like the in the factor, we were using the designations of this reference frame, which is the moving frame, NOA. So we are using these designations, but right here we will use X and Z designation. Sorry, X, Y, and Z, but Y actually we do not need to use. And let me just write this because it's important. And as I said, within these steps, these requirements that we need to attend, we got more steps within. So assign local z-axis and x-axis. And what is important to let clear is that DH representation does not use the y-axis. So we got just checked these first requirements, which is assign these designators, which is the axis z and x, which is the reference frame, okay? And we do not need to use the y-axis. And further, I can tell you why we do not use the y-axis. But from now, it's enough only to know that the H representation doesn't use this axis. And we got even more again within these requirements. So all joints, this is very important. All joints are represented represented by a z-axis if the joint is revolute the z-axis is in the direction of rotation. And if the joint is prismatic, the z-axis is along the direction of the linear movement In each case, the index number for the z-axis for the z-axis of joint n is any minus 1. Okay, like we can see right here, the index of z any minus 1. Okay. Okay, for this first step of the procedure that we need to follow to accomplish our representation with the DH. Uh, so this within steps inside this first step, assign a referential frame to each joint. So we got just covered. Just write this within steps inside this first one. And we got more things to cover of this figure before we start to solve a example to see how we can represent this. And we can already said that is a complex problem. Things like right here you can see this what we call common normal. So let's keep writing the main aspects of this representation. Okay, before we write the important aspects of this illustration, let's first know a bit of what we are left, which is right here. As I already said, right here we got this common normal. What else? We got theta, so is a angle in which we can is the angle of rotation of this first link, and as you can notice, right here is the joint 1, sorry, the joint n. It's not joint 1, joint 2, joint 3. On the method in which we are in, which is DH, we need to name these joints as n. So this one is n, the second one n1 and n2, and just like we are naming these joints, we have this pattern. So if this one is theta n, this one is theta n index n plus 1, and right here to rotate this joint following this pattern, we got theta and on index n plus 2, and which is different of this pattern, and you can notice for this first, um, sorry, following this pattern, this should be the second joint. Um, and again, is the joint as we are assigning, we are naming as n plus 1. Um, the difference is it is that for assign this reference frame, we are using this central joint, and we are assigning naming as the reference frame as Zn, and one joint before we are assigning as Zn minus 1, and one joint after this joint on the center we are assigning as Zn plus 1. Okay, so I think what else? Right here, the normal. Again, we got this normal, and we got this other normal, which is n plus 1. Okay, so now let's write these terminologies that we are using, and also explain a little bit, and after I write what is each of these parameters with its terminology, we will back again on the illustration and explain based on what we are writing. And is again something that is on the book. We are using the text of the book, and it is best. This is the best because on the book we cannot commit a mistake, because yeah, it's the book, it's the words of the book. Okay, so I will write this I think in green color. Okay, so if you notice, the normal, the common normal is perpendicular to any scale line. So there is always one line mutually perpendicular, mutually perpendicular to any scale line. And this is called the common normal. Okay, what else? Of course, now we have to set what is a normal. So the common normal is the shortest distance between the scale line Okay, so the normal is the shortest distance between the scale line. Uh, so is this distance between this axis and this axis. So it's the perpendicular between these axes. It is perpendicular and is the shortest distance between these scale lines. Okay, and let me put dots right here, and we got more. We always assign the x-axis of the local reference frame and the direction of the common normal between the previous and current axis. And open a within comment inside this. If AN represents the common normal between Z and in index any minus 1 and Zn, like we can see right here. So n, Zn, and any minus 1, and the common normal in between this axis is this one. So the direction of xn is along an. Let's check. So we got the axis Zn minus 1, the axis Zn, And in between this axis, we got the common normal AN. So the direction of XN is along AN. Okay, and XN, we are attributing the XN axis on the same direction as the common normal AN. Okay, check it. What else? Okay. Similarly, if the common normal between Zn and Zn plus 1 is An plus 1. So let's see the common normal between Zn and Zn plus 1. Zn plus 1. The common normal in between this axis is the common normal An plus 1. And so the direction of xn plus 1 is the same as an plus 1. I'm saying I'm pronunciating this with this pause, but is n and in index n plus 1, so is a n plus 1. And similarly, right here, sorry for this delay, x in index n plus 1, so is x n plus 1. Okay. So the direction of x n plus 1 will be along a n plus 1. So the key aspect right here, and we can already point, is we always attribute the the x-axis, this axis, we always attribute on the same direction as the common normal. So as you can see right here, we have attributed this x-axis on the same direction as the common normal. The z-axis we are attributing, making point parallel to the direction of rotation. So as you can see, for this first joint N, we are attributing the Z N minus 1 on the same direction as the direction of its rotation, which is theta N. X N plus 1, we are attributing this axis on the same direction as a n plus 1, and the axis z n plus 1 we are attributing on the same direction as its rotation, which is theta n plus 2. So yeah, notice we got a pattern. We got joint n n plus 1 and joint n plus 2. So we got, for its rotation, theta n plus 1, theta n plus 2, but for naming the axis is different. We are not following this pattern. For the first joint, joint n, we got z n minus 1, and this joint on the center, we got zn, and a joint after this one, we got z uh, n plus 1. Okay, and we got even more to cover. And I forgot to mention about this parameter also d, which is the distance on the z-axis between two successive common normals. So we got this common normal an, we got this other common normal an plus 1, and that is the distance between these two normals, these two common normals. So let me write this right here. I mentioned theta, but I do not write anything about it. And let's do this right now. But first, d represents the distance on the z-axis between two successive common normals. And also, I do not wrote about, let's see, if n, I wrote what is a common normal, okay. Let me put this in parentheses, an. And to be more exactly detailing the common normal, again, is the shortest distance between the skill line, but is also at the same time the shortest distance um, is the shortest distance between the skill line, these lines, this axis, and also the length of this link. Is the length of the link shortest distance of the skill line and I will put between parentheses axis. Axis. And also the length of the links of one link. and we got other common line, common normal, sorry, we got other common normal to the other link. We even got this, as I'm about to write about the data, I will write about alpha as well. We got this angle right here, alpha. So first, about data. Represents the rotation about the z-axis. And alpha represent the angle between two successive z-axes. Which is also called twisted angles. Twist angles. So we need to let clear again. DH do not use the y-axis. So DH do not use the y-axis. So we will always attribute local frames and these are the local frames that we will attribute. And do not fool yourself. Zn points, and of course is better again to repeat this, and we will use all those things that I wrote on our first examples, on the resolution of our first examples, to train this, because it's not so intuitive and not so easy at the first time. And xn, and the order is, of course, zn minus 1, zn, xn minus 1. Let me see. We got xn plus 1, zn plus 1, we got zn, we got zn minus 1 also. So I think, is that right? Z, and again, it's not zn, sorry for if I'm pronouncing this with a delay, putting pause. on my pronunciation, is indexed is z n minus 1 x n minus 1 z n x n z n plus 1 and x n plus 1. So z points on the same direction as is rotating, and this is very obviously, this is intuitive. Rotating. So right here we just need to pay attention on the way that is tilted. So pay attention in the way that is tilted. Pointing, z points on the same direction as it is rotating. Data. And x points on the same direction as the common normal. And now let's call this the third step. So I will just name this the third step, and is the step that we can only take if we follow the first two ones. So let's name the third step. And okay, so of course, if we are on the third step, so we assume that we take the first two. Okay. And now the reason why we are taking this third step, which is again, we will get within this step more steps to take. So we need to follow the necessary motions to transform from one reference frame to the next. Assuming we are at the local reference frame z and x and zn. So we can already take this conclusion. This is the local reference frame right here. That is the local reference frame. We do the following sequence of for, and notice this is the standard, so we do for standard motions to get the next local reference frame. X n plus 1 z n plus 1. So we got this example, and just like we are again, it's good if we take something that we already has constructed a knowledge, like we build our knowledge on how to do transformations and represent robots with um, three different coordinate systems, and we use this right here. And now with DH representation, we will do basically the same thing, but with different parameters and namely different these parameters. If this one, if this joint, which is n plus 1, is our local reference frame, if we take these four standard motions, we will get on this another joint, which is the joint n plus 2. And now this joint will be the axis of this joint will be our local reference frame. And for any number of joints, we will do this procedure. So again, we will take these four standard motions that we will list, and doing this, each of one of these joints, the axis of the joints will be the new local reference frame. Okay, yeah, I think this video is very long. So we have covered a bunch of things that we will need from here. to start to represent robots using DH, and I think we are ready to start to solve um, examples to see its solutions. So we saw two steps, which is very important to DH representation, and now this third one, which is this step that we can only take with we got if we take the first two. So this one is very important. So as you can see, we will do a sequence. So let me do this in green. So we will follow a sequence of standard four standard motions to get to the next local reference frame. Okay, so on the next video we will see these four standard motions of this third step, and this way we will solve this problem right here using DH representation. Of course, we can represent this with a transformation equation and followed by matrices, equation with matrices. Okay, so for now, I think it's all. We have covered too much things. And okay, so see you on the next video. Thank you.